Tonight, we're going to explore one of the most fundamental questions human beings have ever asked. How many individual stars truly exist? It might sound like a straightforward query, but the answer we've uncovered is so incredibly vast that it profoundly shifts our understanding of numbers, of immense scales, and of our unique position within the grand cosmic tapestry. By the end of our time together, you'll not only have a clear answer, but also a deeper appreciation for why this knowledge matters and what it tells us about the universe we call home. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Now, let's begin with something you probably do without even thinking about it every single day: estimating quantities. Imagine walking into a small coffee shop. Your brain instantly starts to process the environment, instinctively gauging the number of patrons present. Are there 5 individuals scattered around tables? Perhaps 20 people milling about near the counter. Your internal count is likely quite accurate for smaller groups, probably reliable up to around 15 or 20 individuals. However, once that number grows beyond a certain point, the clarity begins to fade. Does the room hold 40 people or 60? Most of us simply can't tell the difference without actively going through the effort of counting each person. This isn't a flaw in our intelligence. It's simply how human thought patterns developed over countless generations. Our ancient ancestors needed to quickly assess immediate dangers and opportunities in their immediate surroundings. They needed to know, for instance, how many potential threats lurked in the shadows? How many members were there in their own tribal group? How many animals grazed in that distant herd? These vital numbers rarely exceeded a few dozen. Our minds simply never developed the inherent capacity to intuitively grasp thousands, let alone the truly enormous figures like millions or billions. When a news report states that a sports stadium holds 70,000 spectators, your intellect accepts this fact. You understand the meaning of the words. But you don't feel the sheer magnitude of 70,000 in the same visceral way you can easily visualize 5 friends standing right in front of you. This mental disconnect creates a significant challenge when we start talking about the sheer number of stars, because the figures involved are so unbelievably massive that they exist completely outside our natural, intuitive grasp. So, before we can even begin to discuss the total count of stars, we need to establish a mental framework for comprehending truly vast numbers. We need to genuinely sense the difference between a million, a billion, and a trillion. Without that fundamental mental grounding, the final answer will simply register as abstract noise, a collection of digits without any true impact. Consider a million seconds. That translates to just under 11.5 days. You could theoretically count to a million in less than 2 weeks, if you committed to the task without interruption for sleep or food. It would certainly be a grueling marathon, requiring immense dedication, but it's a conceivable undertaking. You can readily imagine dedicating 11 solid days to any demanding task. It fits within the scope of a single human experience. Now, let's stretch that further: a billion seconds. This isn't just a bit longer, it's a monumental leap. A billion seconds clocks in at approximately 32 years. If you were to start counting from the very moment of your birth and never once paused, you would finally reach the 1 billion mark, sometime in your early 30s. The entire span from helpless infant to fully grown adult would be completely consumed by this singular, relentless endeavor. What initially seemed like a substantial figure, when we considered a million, has now expanded into something that encompasses an entire human lifetime, a period filled with personal growth, learning, and countless experiences, all swallowed by the act of counting. But even a billion pales in comparison to a trillion. a trillion seconds stretches out across an unimaginable 1,700 years. To count that high, you would have needed to begin your tally before the invention of agriculture, before the development of written language, before human civilization itself had even started to take root. You would have been diligently counting during the last great ice age, when our species still lived in small, nomadic hunter-gatherer bands traversing ancient landscapes. Every single empire that has ever risen and subsequently fallen throughout recorded history would have come and gone while you continued your count. Every war fought, every peace treaty signed, every technological marvel from the simple wheel to the advanced smartphone, all of it would have occurred during your continuous, solitary tally, and still you wouldn't be finished. The distinction between 1,000,000 and 1,000,000,000 represents a 1,000-fold increase. The difference between 1,000,000,000 and 1,000,000,000,000 is yet another 1,000-fold leap in scale. These aren't just incrementally larger figures. They represent entirely distinct categories of magnitude, shifts in scale that our brains struggle to process intuitively. Now, here's the truly challenging part. When we begin to discuss the actual number of stars that exist throughout the universe, we are dealing with quantities that make even 1,000,000,000,000 seem almost quaint. A small, easily manageable figure. We are talking about hundreds of billions of trillions. These are numbers so astronomically vast that even the comparison to 1,000,000,000,000 fails to adequately convey their true, overwhelming scale. But let's not get too far ahead of ourselves. We should start with what we can actually observe. On a truly clear night, far away from the pervasive glow of city lights, you might be able to discern somewhere between 2,000 and 5,000 individual stars with your unaided eyes. The precise number depends on several factors: your specific location, the keenness of your eyesight, and how long you allow your eyes to fully adapt to the deep darkness. Let's generously estimate around 4,000 stars for our discussion. 4,000 individual stars. That was the entire extent of the cosmos visible to ancient humans. That was the celestial canvas upon which philosophers and early astronomers worked and pondered for thousands upon thousands of years. And here's what's truly remarkable about that small number. Every single one of those 4,000 visible stars, every twinkling point of light you can perceive without a telescope, resides within our very own galaxy. They are not scattered randomly throughout the vastness of the universe. They are all, in fact, relatively nearby in cosmic terms, typically within a few hundred light years of our Earth. When you gaze up at the night sky with your naked eyes, you aren't actually seeing the entire universe. What you are witnessing is merely your immediate cosmic neighborhood, a small bubble within our galactic home. Our home galaxy, the Milky Way, is classified as a barred spiral galaxy. Imagine a colossal flattened disk, almost like an enormous frisbee. Stretching across the middle of this disk is a dense, bar-shaped region, a luminous cosmic spine. From this central bar, graceful spiral arms curve outwards, gently unfurling into the surrounding darkness. Our own sun, along with its orbiting planets, is nestled within one of these grand spiral arms, situated approximately 26,000 light years away from the bustling, brilliant galactic center. To put that in more familiar terms, that distance is roughly 153 quintillion miles, or about 246 quintillion kilometers, from the incredibly dense core, where stars are packed far more tightly together than they are in our comparatively quieter region. When you observe that faint, diffuse band of light arcing across the sky on a truly dark night, that ethereal, milky luminescence that gave our galaxy its poetic name, you are actually looking on through the flat plane of our galaxy's disk. You are witnessing the combined, blended light of millions upon millions of stars, each one too distant and too faint to be individually distinguished by your naked eye. They all merge into a soft, luminous river of starlight flowing across the celestial dome. Everything you can see without any optical aid, every recognizable constellation, every bright, named star, all of it exists within this minuscule bubble of space directly surrounding Earth. The most distant individual star visible without a telescope is approximately 16,000 light-years away. Considering that the Milky Way itself stretches across a staggering 100,000 light-years, you are, at best, seeing less than 1% of our galaxy's total volume. This is precisely where the invention of the telescope fundamentally altered everything. When Galileo Galilei first pointed his rudimentary telescope skyward in 1609, he made a groundbreaking discovery that profoundly shook the established astronomical community. That milky band across the heavens wasn't, as many had long assumed, a cloud of glowing, ethereal gas. Instead, it was composed of countless individual stars, each one too faint for the naked eye to perceive, yet perfectly resolved and distinct through the lens of his primitive instrument. Every subsequent improvement in optical technology brought more revelations. Larger lenses were able to gather significantly more light, unveiling even fainter, more distant objects. Enhanced manufacturing techniques created clearer, more precise images, and the perceived count of stars continued its relentless climb. Thousands of stars became tens of thousands rapidly transformed into millions. So, precisely how many stars are actually contained within our Milky Way galaxy? This question proves to be far more challenging to answer than one might initially imagine, and the inherent difficulty reveals something crucial about the complex task of counting cosmic objects. Firstly, a significant portion of our galaxy remains hidden from our direct view. Enormous, opaque clouds of interstellar dust obscure our line of sight in many directions. When we attempt to peer towards the very center of our galaxy, for example, we are looking through thousands of light-years of this pervasive dust. It's akin to trying to see through an incredibly thick, swirling fog. The light emitted by countless distant stars simply gets absorbed by these dust particles long before it ever has a chance to reach our telescopes on Earth. Secondly, the vast majority of stars are incredibly dim. Red dwarf stars, which are by far the most common type, making up an astonishing 70 to 75% of all stars, are so inherently faint that not a single one is visible to the naked eye, despite their overwhelming abundance. If your eyes could magically perceive all the red dwarfs in our immediate galactic neighborhood, the night sky would appear absolutely packed with stars, thousands upon thousands of them, filling every patch of darkness where you currently see only dozens. Thirdly, and perhaps most fundamentally, we are attempting to measure something from within its own boundaries. Imagine standing deep inside a vast, dense forest and trying to accurately count every single tree. You could count the trees immediately around you with relative ease, but distant trees would quickly become obscured, hidden behind the ones closer to your position. And the forest itself stretches out in every direction, far beyond the limits of your sight. Astronomers employ several ingenious methods to circumvent these inherent challenges. They carefully count stars within small, specific regions where they have exceptionally clear visibility, and then they extrapolate that count by multiplying it across the estimated total area of the galaxy. They also measure the total mass of the galaxy by observing its gravitational effects on orbiting stars and gas, and then they estimate what fraction of that total mass is comprised of stars as opposed to gas, dust, or the enigmatic dark matter. Furthermore, they meticulously study other spiral galaxies that appear structurally similar to our own, using those external galaxies as comparative templates. All these diverse methods carry their own inherent uncertainties, but remarkably, they consistently converge on a very similar, consistent range. The Milky Way galaxy is estimated to contain somewhere between 150 billion and 250 billion stars. Most precise calculations tend to cluster around the figure of 200 billion. 200 billion stars within our galaxy alone. If you were to count them at a steady rate of 1 star per second, without ever pausing, it would take you over 6,000 years to complete the task. You would have had to start counting before the very first pyramids were even constructed in ancient Egypt. Think about what this truly means. On the clearest, darkest night, you might spot around 4,000 stars with your own eyes. But those are just a tiny fraction, swimming in an ocean of 200 billion stars that remain completely unseen by you. For every single star you can visually identify without any aid, there are an astonishing 50 million others that are simply invisible, hidden from your sight. Our home galaxy is far, far more densely populated with these blazing cosmic furnaces than the tranquil night sky ever suggests. Now, things are about to get truly mind-bending. For the vast majority of human history, people had no idea that other galaxies even existed. When early astronomers in the 1700s and 1800s observed fuzzy, indistinct patches of light scattered across the heavens, they labeled them nebulae, a Latin term for clouds. They naturally assumed these were merely clouds of gas and dust, floating within the confines of our own Milky Way. While some of these nebulae indeed turned out to be gas clouds, many others were something far more extraordinary, something that would revolutionize our understanding of the universe. The Andromeda Galaxy itself is visible as a very faint, hazy smudge to the naked eye on exceptionally dark nights. For centuries, it was simply categorized as another one of these enigmatic nebulae. Then, in 1923, a brilliant astronomer named Edwin Hubble made a discovery that completely reshaped our entire concept of the cosmos. Using the powerful 100-inch Hooker telescope at the Mount Wilson Observatory, Hubble identified a special type of star in Andromeda, a Cepheid variable. Cepheid variables are pulsating stars, meaning they regularly brighten and dim in a predictable cycle. These particular stars possess an incredible property. The amount of time it takes them to complete one cycle of brightening and dimming is directly and consistently related to their actual, inherent luminosity, how truly bright they are. So, by carefully measuring the pulsation period of a Cepheid, scientists can accurately determine its true brightness. Then, by comparing that known intrinsic brightness to how bright the star ours appears from Earth, a straightforward calculation reveals its precise distance. When Hubble performed this crucial calculation for the Cepheid he found in Andromeda, he arrived at a truly astonishing result. His initial estimate placed Andromeda at roughly 900,000 light-years away. We now know, with more advanced measurements, that it's actually about 2.5 million light-years distant, or approximately 14.7 quintillion miles, which is roughly 23.7 quintillion kilometers. His initial measurement was a bit off, mainly because he didn't yet have the exact, refined understanding of the period-luminosity relationship for all types of Cepheids. However, the absolutely critical point was established beyond any doubt: Andromeda could not possibly be located within our Milky Way. It was an entirely separate, colossal collection of stars, a completely distinct galaxy, containing hundreds of billions of stars itself, existing far, far beyond the boundaries of our own. The universe, in that singular moment of discovery, became incomparably vaster than anyone had ever dared to imagine. The Milky Way was not the entirety of creation. It was merely one galaxy among countless others. Once astronomers understood what they were truly looking for, They began to find galaxies everywhere they pointed their powerful instruments. Aim a telescope at almost any seemingly empty patch of sky, and you would uncover dozens, hundreds, and sometimes even thousands of individual galaxies. The universe, it turned out, was absolutely teeming with them. But how many are there exactly? And even more importantly for our main question, how many stars did all those galaxies collectively contain? In the 1990s, astronomers embarked on an incredibly ambitious and daring experiment. They directed the mighty Hubble Space Telescope towards an exceptionally tiny, seemingly unremarkable patch of sky located within the constellation Ursa Major, which is also known as the Great Bear. This particular patch appeared completely empty to the naked eye, and even most conventional telescopes showed nothing but blank darkness. It was so incredibly small that you could completely cover it with a single grain of sand held at arm's length against the sky. The Hubble telescope then stared intently at this empty patch for 10 continuous days, diligently collecting every single photon of light that managed to reach its sensitive detectors. The resulting image, a breathtaking mosaic of faint, distant lights, was famously dubbed the Hubble Deep Field, and it proved to be utterly revolutionary. In that minuscule, seemingly vacant patch of sky, Hubble revealed approximately 3,000 distinct galaxies. Imagine that, 3,000 entire galaxies in a region of sky you could obscure with the head of a pin held at arm's length. Most of these galaxies were incredibly distant, billions of light years away. Their ancient light had been traveling for the vast majority of the universe's existence just to reach us. If you do the simple math, if there are 3,000 galaxies in such a tiny sliver of the sky, and you would need about 12 million such regions to completely cover the entire celestial sphere, that mathematical extrapolation suggests the existence of tens of billions of galaxies within the observable universe. Later observations pushed even deeper into the cosmic void. The Hubble Ultra Deep Field, for instance, found an astounding 10,000 galaxies in an even smaller, more distant patch of sky. The Hubble Extreme Deep Field pushed the boundaries further still. And then, in 2016, a dedicated team of scientists meticulously analyzed all the available data from these deep field surveys and arrived at a new, revised estimate. Approximately 2 trillion galaxies reside within the observable universe. This staggering number primarily stems from data gathered between 2010 and 2020. The new James Webb Space Telescope, which began its operations in 2022, is still in the process of refining these estimates, peering deeper and with greater clarity than ever before. Early results from the JWST suggest that this 2 trillion figure is broadly in the correct ballpark, though it's possible some very distant, incredibly faint populations of galaxies might have been missed in earlier surveys. So, for now, we can consider this our best current estimate, accurate to within perhaps a factor of 2 or 3. 2 trillion galaxies, each one containing anywhere from a few billion to over a trillion individual stars. The diversity among these galactic structures is truly staggering. We have tiny dwarf galaxies holding only a few billion stars. Then there are grand spiral galaxies, much like our own Milky Way, brimming with a few 100 billion stars. And at the largest end of the spectrum, there are colossal elliptical galaxies, each boasting several trillion stars. What then is a good average? If we account for the stellar mass and the many smaller, harder to detect galaxies that we know exist, the typical galaxy probably contains somewhere between 70 and 100 billion stars. Let's use 100 billion as a convenient, rounded figure for our calculations, acknowledging that this is an approximation. So, if we multiply 2 trillion galaxies by 100 billion stars per galaxy, we arrive at the truly mind-boggling total of 200 billion trillion stars. Written out fully, That number looks like this: 200 followed by 21 zeros. In scientific notation, it's expressed as 2 multiplied by 10 to the power of 23. Let me attempt to give you some sense of the sheer scale of this number. Though I must warn you up front, it's not truly possible for our human minds to grasp it intuitively. The number is simply too vast, but we can at least try to gesture towards its incredible magnitude. Consider this comparison. There are approximately 7.5 quintillion grains of sand on all of Earth's beaches combined. That's 7.5 billion trillion grains. For every single grain of sand found on every beach across our entire planet, there are roughly 27 stars scattered throughout the observable universe. Some popular science explanations might round this up to 30 stars per grain, while others suggest closer to 10. The precise ratio depends on which specific estimate for the number of sand grains you use, but the overall order of magnitude is undeniably correct. We're talking about roughly 10 to 100 stars for each individual grain of beach sand on Earth. Imagine picking up a handful of sand the next time you're at the beach. In that small collection, you might be holding a few thousand grains. For each one of those tiny, seemingly insignificant specks, there are dozens of colossal, blazing stars spread across the immense expanse of the cosmos. Each of these stars is a massive ball of nuclear fire, very likely surrounded by its own retinue of planets, all existing within a galaxy somewhere in the observable universe. If every single person currently alive on Earth were to start counting stars right now, and each person counted 1 star per second without pausing for sleep or rest, it would take the entire human species nearly 800 years to count them all. Generations would be born, live their lives, and pass away during this continuous count. Entire civilizations could rise and fall, and we would still be counting. But here's what makes this number even more extraordinary, even more profound. That figure, 200 billion trillion stars in the observable universe, might actually be a dramatic undercount of the total number of stars that truly exist. The observable universe is specifically defined as the region of space from which light has had sufficient time to reach us since the Big Bang, the beginning of our universe. Our universe is estimated to be about 13.8 billion years old. Light travels at an incredible speed, approximately 186,000 miles per second, or 300,000 kilometers per second. You might logically assume, then, that light could only have traveled 13.8 billion light years in 13.8 billion years. However, there's a crucial factor. The universe itself has been continuously expanding while that light was making its journey. Space itself has been stretching, carrying galaxies along with it. By the time light from extremely distant objects finally reaches our telescopes, those objects have moved significantly farther away than they were at the moment the light was originally emitted. The true edge of the observable universe, therefore, isn't 13.8 billion light years away. It's actually much farther, approximately 46.5 billion light years in every single direction. This means the observable universe has a staggering diameter of about 93 billion light years, which translates to roughly 546 sextillion miles, or approximately 879 sextillion kilometers. This represents our cosmic horizon. Beyond this immense distance, light simply hasn't had enough time to reach us yet. It's not that those regions of space don't exist. It's just that the light from them is still in transit, or in some extreme cases, will never reach us at all, because the expansion of space itself is accelerating faster than light can traverse it. Here's the critical, philosophical question that arises from this understanding. Does the universe simply end at the boundary of our observable universe, or does it continue indefinitely beyond that horizon? Most of the available evidence strongly suggests that it continues, possibly much, much farther, perhaps even infinitely far. If the universe is truly infinite in its extent, then the total number of stars within it would also be infinite. I mean literally infinite. Not just an incredibly large number, but an endless, boundless quantity. There would be infinitely many galaxies, each containing billions or trillions of stars, stretching on forever in every conceivable direction. In such an infinite universe, every single possible configuration of matter would inevitably occur somewhere within that boundless expanse. And not just once, but it would occur infinitely many times. This means there would be infinitely many galaxies, absolutely identical to our Milky Way. Infinitely many planets precisely identical to Earth. Infinitely many versions of you, reading these exact words right now, in infinitely many identical universes. This sounds like the wildest science fiction scenario, but it is a serious and profound implication of an infinite universe with a roughly uniform distribution of matter. If space truly extends forever, and matter is, on average, spread out evenly, then every possible arrangement of atoms must eventually repeat itself. We simply do not know if the universe is actually infinite. We cannot see beyond the boundaries of our observable universe, so we are unable to directly measure whether space continues indefinitely or eventually curves back on itself. Current cosmological models are consistent with either a finite but extremely vast universe or an infinite one. The available data does not yet allow us to definitively distinguish between these two profound possibilities. What we can state with a high degree of confidence is that the observable universe, the part we can actually perceive, contains approximately 200 billion trillion stars. Everything beyond that specific count remains within the realm of speculation, albeit educated speculation built upon our very best understanding of cosmology. Let's shift our perspective slightly and focus on what these stars actually are in their fundamental nature. Because truly understanding their composition and processes makes their sheer numbers even more astonishing and impressive. A star is essentially a massive sphere of plasma. Plasma is a state of matter so intensely hot that electrons are stripped away from their atoms, creating an ionized gas. This superheated plasma is held together by the star's own immense gravitational pull. And deep within its core, if the star possesses enough mass and is sufficiently hot, a process called nuclear fusion occurs. Our own sun, for instance, primarily fuses hydrogen atoms into helium in its fiery core. Every single second, a staggering 600 million metric tons of hydrogen are converted into helium. In this incredible process, approximately 4 million metric tons of that mass are directly transformed into pure energy, following Albert Einstein's famous equation, EmC_dI. That immense energy then slowly, gradually works its way from the sun's scorching core to its surface over thousands of years, constantly bouncing between countless particles in the incredibly dense interior, before finally radiating outwards into space as visible light and heat. The tiny photon of light that gently touches your face on a sunny day was actually created deep within the sun's core tens of thousands of years ago. The sun has been diligently performing this nuclear alchemy for about 4.5 billion years, and it is projected to continue doing so for another 5 billion years before it finally exhausts its core hydrogen fuel. At that point, it will begin to swell dramatically, transforming into a colossal red giant star, likely engulfing the inner planets Mercury and Venus, and possibly even our own Earth. Eventually, it will shed its outer layers, sending them drifting into space, and leave behind a small, dense remnant called a white dwarf, which will slowly cool over many trillions of years. This entire description is for just one star, one incandescent ball of plasma tirelessly converting mass into energy through nuclear fusion. And yet, There are an estimated 200 billion trillion of them. The total power output from this multitude of stars is almost beyond comprehension. Our Sun alone produces about 380 trillion watts of power. If every star produced a similar amount of power, which is a reasonable average, the total energy output across the observable universe would be approximately 7.6 multiplied by 10 to the power of 40, 9 watts. That's a mind-boggling 6,000 billion trillion watts of energy constantly flooding through space. Of course, not all stars are exactly like our Sun. They exhibit a truly spectacular range of sizes, temperatures, colors, and lifetimes. Red dwarf stars, as we mentioned, are the most common, making up 70 to 75% of all stars. They are relatively small, with masses typically between 8% and 50% of the Sun's mass, and they burn their nuclear fuel incredibly slowly and efficiently. A red dwarf can shine steadily for trillions of years. In fact, none that have ever formed in the universe have died yet, simply because the universe itself isn't old enough. Every single red dwarf star ever born is still glowing today. If 3/4 of our 200 billion trillion stars are red dwarfs, that means there are about 150 billion trillion red dwarfs scattered across the cosmos. None of them are visible to the naked eye from Earth, despite being the most numerous stellar type in existence. Yellow dwarf stars, like our Sun, represent a much smaller fraction, making up about 7 to 8% of all stars. These main, sequence stars typically live for roughly 10 billion years before beginning their death throes. Even so, that still translates to approximately 14 billion trillion Sun-like stars existing within the observable universe. Then we have the truly massive stars, the brilliant blue and white giants and supergiants. Some of these colossal stars can be over 100 times the mass of our Sun. These are relatively rare, perhaps constituting only 1% of all stars, but they are spectacularly bright. A single massive blue star can easily outshine 100,000 suns. These stars live incredibly fast and die dramatically young, exploding as cataclysmic supernovae after only a few million years. The very most massive stars might only last for a few million years. They are so rare and short-lived that at any given moment, there might only be a few billion of them scattered across the entire observable universe. That sounds like a large number until you remember it's a tiny fraction of the total stellar population. Beyond the actively fusing stars, we also have stellar corpses. These include white dwarfs, which are the slowly cooling remnants of stars similar in size to our Sun. Then there are neutron stars, the incredibly dense, crushed cores left behind after massive stars explode as supernovae. And finally, there are black holes, the ultimate collapsed remnants of the most massive stars, where gravity has become so overwhelmingly powerful that not even light itself can escape its grasp. These objects are no longer actively fusing elements, but they are still very much present, still integral parts of the cosmic census. When we talk about counting stars, we are counting all of these newborn stars just forming from swirling gas clouds, middle-aged stars steadily fusing hydrogen, dying giants in their final fiery stages, and all the various stellar remnants. The comprehensive number includes the full, magnificent diversity of stellar evolution, from the moment of birth to the final stages of death. Now, let's talk about planets. Because stars rarely exist in complete isolation, most are accompanied by their own intricate planetary systems. Until 1995, humanity knew of only one planetary system, our own. We strongly suspected that other stars must also possess planets, but we simply lacked the technological means to detect them. Then, in that pivotal year, astronomers announced the discovery of the first confirmed planet orbiting a sun-like star other than our own. It was a gas giant, roughly half the mass of Jupiter, orbiting incredibly close to its parent star. Since that breakthrough, the pace of discoveries has absolutely exploded. The Kepler Space Telescope, operational from 2009 to 2018, revolutionized exoplanet hunting. It found thousands of exoplanets by meticulously observing stars and detecting the tiny, subtle dimming that occurs when a planet passes directly in front of its host star, partially blocking its light. As of 2025, we have confirmed the existence of over 6,000 exoplanets, with many thousands more candidates awaiting rigorous verification. This rapidly accumulating data reveals something truly remarkable: planets are incredibly common. Very, very common indeed. It appears that most stars host at least one planet. Many, in fact, possess multiple planets, forming entire complex systems. The formation of planetary systems seems to be a default outcome of the star formation process, rather than a rare or unusual exception. If most of the 200 billion trillion stars in the observable universe possess planets, then the total number of planets likely far exceeds the number of stars. There could be 300 billion trillion planets, perhaps even more. The universe is not merely filled with stars, it is absolutely teeming with worlds. We are, of course, particularly interested in rocky planets that reside within the habitable zones of their host stars. These habitable zones are the specific regions around a star where temperatures are just right to allow for the existence of liquid water on a planet's surface. And liquid water, as far as we know, is absolutely essential for life to exist. Based on the extensive data collected by the Kepler mission, rough estimates suggest that anywhere from 20 to 50% of Sun-like stars possess at least one rocky planet within their habitable zone. Let's adopt a conservative estimate and say 20%. 20% of those 14 billion trillion Sun-like stars translates to approximately 3 billion trillion potentially habitable planets. That's 3 million billion worlds where the fundamental conditions might be just right for life to emerge. Now, that doesn't automatically mean all these planets actually harbor life. Habitability requires more than just the right temperature range. You would need the correct atmospheric composition, robust protection from harmful stellar radiation, sufficient geological activity to recycle vital nutrients, probably a strong planetary magnetic field, and likely many other complex factors that we don't yet fully comprehend. But even if only a minuscule fraction of these potentially habitable worlds actually develop life, the sheer absolute numbers could still be utterly staggering. If, for instance, only 1 in a million habitable planets actually gives rise to life, that still leaves us with 3 quadrillion living worlds. If 1 in a billion of those worlds then develops intelligent life capable of building advanced civilizations, that still equates to 3 trillion technological societies scattered across the cosmos. These are, of course, highly speculative figures. Our current sample size for life is precisely 1 Earth. We have absolutely no idea how common or how rare the spontaneous origin of life actually is. We don't know the precise odds of evolution ultimately producing intelligence. We also don't know how long technological civilizations typically endure before they either destroy themselves or simply die out. But the crucial takeaway is the sheer number of opportunities. With planets numbering in the hundreds of billions of trillions, even extremely low probabilities for life's emergence and evolution could still result in a vast abundance of life throughout the universe, simply through the powerful law of large numbers. And yet, despite these astronomical possibilities, we have so far found no conclusive evidence of other life. No clear radio signals, no giant megastructures, no obvious signs of advanced industrial civilizations. The universe, in all its immense glory, appears profoundly silent to us. This perplexing silence is famously known as the Fermi paradox named after the physicist Enrico Fermi, who famously posed the question, "Where is everybody?" If there are billions or even trillions of potential habitats for life, and the universe has existed for 13.8 billion years, providing ample time for life to arise and evolve, then we should, logically, be seeing clear evidence of other civilizations. The fact that we don't is deeply puzzling. Perhaps life is extraordinarily rare, and we are truly alone, or nearly alone, in this vast cosmic ocean. Perhaps intelligence is the exceptionally rare step in evolution. Perhaps civilizations inevitably destroy themselves, unable to navigate the challenges of their own technology and growth. Maybe they are deliberately hiding from us, part of a galactic federation observing us from afar. Or perhaps the immense distances between stars are simply too vast for any practical contact to occur, making interstellar communication and travel prohibitively difficult. We simply do not know the answer. What we do know with certainty is that the sheer number of stars and planets provides ample, almost boundless opportunity for life to exist elsewhere, even if we haven't found it yet. Let's now consider how stars are responsible for creating the very elements that make planets and life possible, because this connects us directly to those 200 billion trillion stars in an incredibly profound and intimate way. In the first few minutes after the Big Bang, the universe was incredibly hot enough for nuclear fusion to occur throughout all of space, not just confined to the cores of stars. This primordial fusion created only three elements: hydrogen, helium, and tiny trace amounts of lithium. That was it. 3 elements in total. Everything else, every single other element on the periodic table that we know and interact with, was created later, inside the fiery hearts of stars. The fundamental elements of life, such as carbon, nitrogen, and oxygen, were forged in the cores of stars through sustained nuclear fusion. Heavier elements, like iron and nickel, were created in the final, intense stages of massive stars' lives. The very heaviest elements, precious gold, rare platinum, and radioactive uranium, were synthesized in the unimaginable violence of supernova explosions and the even more extreme collisions of neutron stars. Stars are, quite literally, cosmic element factories. They take simple hydrogen and helium and fuse them together into progressively heavier and more complex elements. When massive stars reach the end of their lives and explode, they violently scatter these newly created elements into the surrounding space. That enriched material then mixes with existing gas clouds, and eventually, these enriched clouds collapse to form new generations of stars and planets. This grand cosmic cycle has been continuously operating for over 13 billion years. Each successive generation of stars enriches the cosmos slightly more than the last. The very first stars contained almost pure hydrogen and helium. Our Sun, which formed about 4.5 billion years ago, contains approximately 2% heavy elements by mass. That seemingly small percentage made our Earth possible. Rocky planets, by their very nature, require these heavier elements. And life, as we understand it, absolutely requires carbon, oxygen, nitrogen, phosphorus, and many other complex elements. Every single atom in your body, with the sole exception of the hydrogen atoms, which originated in the Big Bang, was created inside a star. The oxygen you breathe right now was forged in stellar cores billions of years ago. The calcium that forms your bones came from the remnants of dying stars. The iron that carries oxygen in your blood was synthesized in the cataclysmic explosions of supernovae. You are, quite literally, made of processed stardust. This isn't just poetic language, it is a fundamental chemical fact. The atoms that compose your very being were created through nuclear fusion deep within stellar interiors, then scattered into space when those ancient stars died. These atoms were subsequently incorporated into a vast gas cloud that eventually collapsed to form our Sun and its planets. they accreted onto the nascent Earth, and ultimately became an integral part of living organisms, including you. With 200 billion trillion stars operating as ceaseless element factories over billions of years, the universe has produced staggering quantities of heavy elements. There is enough carbon for countless rocky worlds, enough oxygen for atmospheres and oceans on billions of planets, enough silicon and iron for planetary crusts and cores across the entire cosmos. The sheer number of stars directly translates to the total chemical enrichment of the universe. More stars mean more fusion, more element production, and therefore, more raw material available for complex chemistry and, potentially, for life itself. Let's zoom out further and examine how these immense numbers of stars are distributed across space. Because they aren't simply scattered randomly or uniformly. They are organized into intricate structures at multiple, hierarchical scales. Stars first cluster together into galaxies. These galaxies then cluster into larger formations known as groups and clusters. These clusters, in turn, organize themselves into even grander structures called superclusters. And finally, superclusters arrange themselves along vast, interconnected filaments, separated by enormous, almost empty voids of space. Our own Milky Way galaxy belongs to a collection known as the Local Group, which contains about 54 galaxies. Aside from the Milky Way and the Andromeda Galaxy, most of the other members are smaller dwarf galaxies, each with only a few billion stars. The Local Group itself is part of an even larger structure called the Laniakea supercluster, which encompasses approximately 100,000 galaxies spread across a colossal 520 million light-years, or about 3 quadrillion miles, roughly 4.9 quadrillion kilometers. Laniakea is not gravitationally bound in the same way a galaxy or a cluster is. Instead, it is defined by the collective motions of its member galaxies, all drifting towards a common gravitational center known as the Great Attractor. If you could somehow map the entire observable universe, it would reveal a breathtaking structure that resembles a cosmic web. Filaments of galaxies, like luminous, interconnected strands, weave through the darkness, with enormous bubble-like voids separating them. This large-scale structure bears a remarkable resemblance to soap foam. Galaxies are concentrated in thin sheets and filaments, much like the soap film itself, while the vast voids are analogous to the air inside the bubbles, almost entirely empty of matter. This intricate structure originated from tiny, infinitesimal density fluctuations that existed in the very early universe. Slightly denser regions, through the relentless pull of gravity, attracted even more matter, becoming denser still, while less dense regions gradually lost matter to their more massive neighbors. Over billions of years, this process sculpted the universe into the magnificent web of filaments and voids we observe today. The largest known structure in the universe is called the Hercules, Corona Borealis Great Wall, a breathtaking filament of galaxies stretching an astonishing 10 billion light-years long, which is roughly 59 octillion miles, or approximately 95 octillion kilometers. Its sheer size is so immense that it even challenges our current understanding of how cosmic structures form and evolve. So, when you consider those 200 billion trillion stars, remember that they are not evenly distributed throughout space. The vast majority of them reside along these cosmic filaments and are concentrated in the bustling clusters found at the intersections of these filaments. The enormous voids, by contrast, contain relatively few galaxies and therefore relatively few stars. If you were to randomly select a point in space, you would most likely find yourself in one of these vast voids, incredibly far from any galaxy. The universe, despite its countless stars, is overwhelmingly empty. Stars, for all their unimaginable numbers, occupy only a minuscule fraction of the total volume of space. Let's contemplate the future for a moment Because the total number of stars won't remain absolutely constant. Stars are constantly being born and constantly dying, and the delicate balance between these two processes is slowly shifting. Star formation across the universe reached its peak rate approximately 10 to 11 billion years ago, when the universe was only about 3 billion years old. At that ancient time, galaxies were generally smaller, denser, and much richer in gas. Stars were forming at a furious, prodigious pace. Since that cosmic peak, the rate of star formation has steadily declined. Much of the available gas, the raw material for new stars, has either been consumed by past star formation events or dispersed into the intergalactic medium. The remaining gas is less efficient at collapsing to form new stars. Currently, our own Milky Way galaxy forms only about 3 to 5 new stars each year. That might seem like a small number, but if you multiply that across 2 trillion galaxies, you still arrive at trillions of new stars being born annually across the observable universe. Eventually, however, the rate of star formation will slow down even further and then, ultimately, cease entirely. Galaxies will gradually exhaust their reserves of gas. The very last stars will likely form, perhaps a trillion years from now, give or take a few 100 billion years. After that distant epoch, no new stars will ever be born. Existing stars will continue to shine for a while longer. The long-lived red dwarfs, for example, will persist for many trillions of years, but eventually, even they will burn out. In about 100 trillion years, star formation will have completely ended, and most of the existing stars will have finally burned out. The universe will become a much darker, colder place, populated primarily by the remnants of dead stars, white dwarfs, brown dwarfs, neutron stars, and black holes. In the extremely far future, measured in timescales that make the current age of the universe seem like a mere blink of an eye, the very last stars will finally fade into darkness. The universe will descend into a profound, eternal night. But that future is so incredibly distant, so far beyond our immediate comprehension, that it's almost meaningless to truly contemplate. For now, and for billions of years to come, stars will continue to illuminate the cosmos. The number we count today will remain roughly stable, shifting only slightly as stars are born and die, but maintaining the same astounding order of magnitude. Let's bring our focus back to Earth and consider what all of this vastness means for us personally. You are standing on a small planet, orbiting one star among 200 billion trillion. Your sun is, in every cosmic sense, utterly typical, a yellow dwarf of average size and brightness. Your location is completely unremarkable, nestled in the quiet suburbs of a standard spiral galaxy, itself residing in an ordinary, unextraordinary part of the universe. From a purely cosmic perspective, you are, by all measures, utterly insignificant. Your entire civilization has existed for perhaps 10,000 years, if we are incredibly generous in our definition. Modern industrial society, with all its technological marvels, is only about 250 years old. We've only known about the existence of other galaxies for barely 100 years. In cosmic terms, we truly just got here. And yet, despite our fleeting existence and our humble origins, we have somehow managed to measure the universe. We have, in a sense, counted the stars. We have calculated the immense distances to galaxies billions of light years away. We have begun to understand our intricate place within this colossal cosmic structure. We are tiny and brief, yes, but we are also uniquely capable of comprehending the very immensity that contains us. That particular capability is truly extraordinary. We are, in essence, matter that has become conscious of itself. We are atoms arranged in such a way that they can ponder the fundamental nature of other atoms. We are products of the universe that can actually understand the universe that created them. When you look up at the night sky, you are seeing photons of light that have traveled for years from distant stars. The light from Sirius, one of the brightest stars in our sky, departed its source 8.6 years ago when you were younger. The light from Betelgeuse, that fiery red giant, began its journey 550 years ago, during the European Renaissance. These are ancient photons, completing journeys measured in centuries, simply to enter your eye and be absorbed by your retina, creating the profound sensation of seeing a star. You are connected across unimaginable distances in space and vast stretches of time to those distant suns. The very atoms in your body were forged in stars that lived and died before our sun even existed. You are made of materials created inside some of those 200 billion trillion stars, recycled through multiple generations of cosmic processes, eventually ending up on Earth and being incorporated into the living tissue that makes you, you. This perspective can be profoundly humbling. Your individual problems, whatever they may be, occur on one small world among countless other worlds. Your personal concerns are temporary and utterly local in the grand scheme of things. The universe, in its vast indifference, simply does not notice your struggles. Yet, this same perspective can also be incredibly freeing. You do not carry the weight of cosmic significance on your shoulders. You are allowed to be small. You are allowed to experience small joys and small sorrows. You don't need universal importance to matter. You matter to yourself, and you matter immensely to those around you. And that, in itself, is more than enough. Understanding the sheer number of stars provides this crucial context. You are an integral part of something truly vast and ancient, but you are also here, now, experiencing this unique moment. That experience holds intrinsic value regardless of any cosmic scale. Let's bring this part of our exploration to a close by reflecting on the incredible journey we've undertaken so far. We began with a seemingly simple question: how many stars exist? The answer, meticulously refined through decades of patient observations with increasingly powerful telescopes, and continuously updated with the latest, most precise data from groundbreaking missions, like the James Webb Space Telescope, is approximately 200 billion trillion stars in the observable universe. This staggering number arises from the estimated 2 trillion galaxies that we can perceive, each of which contains, on average, around 70 to 100 billion stars, although with enormous variations in size and stellar population. This is our best current estimate as of 2025. It may, of course, be adjusted slightly as the James Webb Space Telescope and future instruments probe even deeper into the cosmos, potentially finding faint galaxy populations that we've missed. However, the overall order of magnitude is considered solid. We are talking about a figure somewhere in the range of 1 to a few hundred billion trillion stars. That number is larger than the total number of grains of sand on all of Earth's beaches, by a factor of roughly 20 to 100. It's larger than the total number of humans who have ever lived on this planet, by a factor of about 2 million. It's a number so immense that counting them individually at a rate of 1 per second would take far longer than the current age of the universe itself. Each one of these stars is a massive, self-sustaining fusion reactor, diligently converting hydrogen into helium and progressively heavier elements, constantly pumping immense energy into space, very possibly hosting its own complex systems of planets, and potentially fostering life. Each star has its own unique story, from its violent formation within a collapsing gas cloud to its eventual dramatic death as a white dwarf, a neutron star, or a black hole. And all of this, all 200 billion trillion stars, exists within the boundaries of the observable universe, the region from which light has had sufficient time to reach us. Beyond that cosmic horizon, there may be vastly, unimaginably more. The universe itself might be infinite, containing an endless supply of stars, Or it might be finite but significantly larger than what we can currently see. We simply don't know yet. But before we fully conclude, let's delve into several other crucial aspects of stars and galaxies that will undoubtedly deepen your appreciation for this cosmic census. Understanding precisely how stars form, live, and die, how we actually manage to measure the immense distances to galaxies, and the different types of galaxies that populate the cosmos will transform that abstract number into something far more tangible and meaningful. Let's start with star formation, because every single one of those 200 billion trillion stars was born from a colossal cloud of gas and dust. The process is both incredibly elegant and intensely violent. Stars are born within what are known as molecular clouds, which are vast, cold regions of space filled predominantly with hydrogen gas and tiny dust particles. These clouds are remarkably cold, typically hovering around -430 degrees Fahrenheit or -250, 7 degrees Celsius, just a few degrees above absolute zero. They appear dark to our eyes because the dense dust within them effectively blocks visible light, though infrared telescopes possess the remarkable ability to peer through these opaque veils. Some molecular clouds are truly enormous. The Orion Molecular Cloud Complex, for instance, spans hundreds of light years across and contains enough raw material to form over 100,000 stars, each similar in mass to our own Sun. You can actually see a portion of this massive complex with your naked eye, the middle star. In Orion's sword isn't a star at all, but rather the glowing Orion Nebula, a bustling stellar nursery where new stars are actively forming right at this very moment. Here's how this incredible process unfolds. Something in the cosmic environment disturbs the delicate balance of the molecular cloud. Perhaps a nearby supernova explosion sends a powerful shock wave rippling through space, compressing the gas. Maybe two molecular clouds gently collide, or perhaps a region of the cloud simply becomes dense enough that its own self, gravity, begins to take over. Whatever the specific trigger, a localized region within the cloud starts to contract, pulling material inward. As this gas falls in, seemingly counterintuitively, it actually heats up. Think of it this way: gravity converts the gas's potential energy into kinetic energy. The individual gas particles move faster and faster as they fall inward, and temperature, at its most fundamental level, is simply a measure of how fast those particles are moving. Faster motion directly translates to a higher temperature. The contracting region often fragments into multiple smaller clumps, each one destined to become an individual star. The center of each of these nascent clumps grows progressively hotter and denser as more and more material continues to fall in. Eventually, the temperature and pressure at the very core become so extreme, so immense, that nuclear fusion can finally begin. Hydrogen nuclei, under these crushing conditions, overcome their natural electrical repulsion and fuse together, forming helium and releasing an absolutely tremendous amount of energy. At this precise moment, a star is officially born. The outward pressure generated by the energy from this fusion process perfectly balances the inward pull of gravity. The newborn star achieves a stable equilibrium and can then shine steadily for millions or even billions of years, its lifespan heavily dependent on its initial mass. This stellar birth process often leaves behind a swirling, rotating disk of leftover material orbiting the brand new star. This protoplanetary disk is precisely where planets will eventually form. Tiny dust particles within this disk begin to collide and stick together, gradually growing from microscopic sand grains into pebbles, then boulders, then mountain-sized objects, then moon-sized bodies, and finally, into fully formed planets. The entire process of planet formation can take maybe 10 million years for rocky planets, and possibly even longer for the larger gas giants. This cosmic drama is playing out across the universe constantly. Right now, in molecular clouds scattered throughout the cosmos, gravity is relentlessly pulling gas together. Protostars, the embryonic stages of stars, are forming. Disks of material are slowly coalescing into the building blocks of planets. In our Milky Way galaxy alone, several new stars are born every single year. Multiply that across 2 trillion galaxies, and you arrive at trillions of new stars being born annually throughout the observable universe. However, the rate of stellar birth has varied dramatically over the long expanse of cosmic history. In the very early universe, the first stars formed from nearly pure hydrogen and helium, the only elements available after the Big Bang. These population errant stars, as they are sometimes called, were likely extraordinarily massive, perhaps 100 to 1,000 times the mass of our Sun. They lived incredibly fast, burned with astounding brilliance, and exploded as powerful supernovae after only a few short million years. Those cataclysmic explosions scattered the very first heavy elements into space: carbon, oxygen, silicon, iron, elements created through fusion in their stellar cores and further synthesized in the violence of the supernova itself. These newly forged elements then mixed with the pristine, primordial hydrogen and helium. The next generation of stars formed from this slightly enriched material, and over billions of years, through countless cycles of stars being born and dying, the universe became progressively more and more enriched with heavy elements. By the time our Sun formed 4.5 billion years ago, the local gas cloud from which it condensed contained about 2% heavy elements by mass. That seemingly small percentage made all the difference. Those heavier elements were absolutely essential for rocky planets like Earth to form, and they provided the necessary raw materials for the complex chemistry that ultimately led to life. Today's star-forming regions produce stars with a wide range of masses, following what astronomers call the initial mass function. The vast majority of stars are small red dwarfs. Fewer are Sun-like yellow dwarfs, and truly massive stars are quite rare. This distribution of stellar masses appears to be fairly universal, holding true across different galaxies and different epochs of cosmic history. Now, let's delve into stellar evolution, because stars don't remain static throughout their lives. They undergo dramatic transformations, and their specific evolutionary path is heavily dependent on their initial mass. Understanding these changes helps us explain the incredible diversity we observe among stars. Consider a star like our Sun. For approximately 10 billion years, it diligently fuses hydrogen into helium in its core. This is known as the main sequence phase, the long, stable period that constitutes the majority of a star's existence. During this time, the energy generated by nuclear fusion perfectly balances the inward pull of gravity, allowing the star to shine steadily and predictably. Eventually, however, the core of the star runs out of hydrogen fuel. Fusion ceases at the very center, and without that outward pressure to counteract gravity, the core begins to contract. This contraction, paradoxically, causes the core to heat up significantly. Meanwhile, hydrogen fusion continues in a shell surrounding the now inert helium core. The energy produced by this shell fusion is actually greater than the energy the star was producing during its main sequence phase, and this excess energy causes the star's outer layers to expand dramatically. The star transforms into a red giant. Its surface cools, which is why it takes on a reddish hue, but its overall size increases enormously. Our Sun, when it becomes a red giant, will swell to about 100 times its current diameter, likely engulfing Mercury and Venus. Earth might technically survive, though it would be scorched and utterly lifeless. As the core of the red giant continues to contract and heat, it eventually reaches a point where it becomes hot enough to ignite helium fusion, converting helium into carbon and oxygen. For stars like our Sun, this helium ignition happens in a sudden, violent event called the helium flash. For more massive stars, helium fusion begins more gently. Either way, the star now possesses two active fusion zones, helium fusing to carbon and oxygen in the core, and hydrogen fusing to helium in a surrounding shell. This particular phase doesn't last for an astronomically long time, perhaps only a few 100 million years. When the helium fuel in the core is exhausted, the core contracts once again. For stars like our Sun, this marks the end of all nuclear fusion. The core simply isn't hot or massive enough to ignite carbon fusion. Instead, it becomes a white dwarf, a super, dense ball of carbon and oxygen, roughly the size of Earth, but containing about half the Sun's original mass. The star's outer layers gently drift off into space, creating a breathtaking phenomenon called a planetary nebula. Despite the name, planetary nebulae have absolutely nothing to do with planets. Early astronomers, viewing them through small, less powerful telescopes, thought they resembled the faint, round disks of planets, hence the misnomer. They are, in reality, beautiful, expanding shells of glowing gas, pushed away by the intense radiation emanating from the dying star's incredibly hot, exposed core. The white dwarf itself will then slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. However, the universe isn't nearly old enough yet for any black dwarfs to have formed. Every white dwarf that has ever come into existence is still slowly glowing. Now, let's consider a much more massive star, perhaps 10 times the mass of our Sun. Its early stages are somewhat similar, a main sequence phase fusing hydrogen to helium, followed by a red giant phase. But massive stars possess enough core mass to continue their nuclear burning cycles much further. After helium burning, the core contracts and heats up sufficiently to fuse carbon, then oxygen, then neon, magnesium, silicon, and finally iron. Each successive fusion stage produces elements with progressively higher atomic numbers, building up the periodic table within the star. And each stage happens much faster than the last. A massive star might spend millions of years fusing hydrogen, then perhaps 1,000,000 years fusing helium, then thousands of years on carbon, hundreds of years on oxygen, perhaps only a year on silicon, and then a mere few days fusing silicon into iron. The final stages of these stellar lives unfold with incredible rapidity. Iron marks the definitive end of the fusion chain. Fusing iron, unlike all previous elements, doesn't release energy, it actually consumes energy. So, when the core of a massive star fills with iron, there's no more fuel to sustain the outward pressure. With no fusion energy pushing outwards, gravity utterly wins the battle. The core collapses in less than a second, shrinking from roughly the size of Earth to a compact sphere only about 12 to 15 miles or 20 to 25 kilometers across. Under this unimaginable pressure, electrons and protons are crushed together, forming neutrons. The collapse is halted only when the core becomes an incredibly dense neutron star. This object is so dense that a single teaspoon of neutron star material would weigh an astonishing 900 billion kilograms on Earth. The collapse happens so catastrophically quickly that the star's outer layers are still falling inward when the neutron-rich core suddenly rebounds. This infalling material violently slams into the rebounding core and is blasted back outward in the most powerful explosion in the universe, second only to the Big Bang itself, a supernova. For a few intense weeks, a single supernova can briefly outshine an entire galaxy. It releases more energy in that short period than our Sun will produce in its entire 10 billion year lifetime. The explosion violently scatters the star's outer layers, laden with newly forged heavy elements, into space at speeds of 10,000 miles per second, or 16,000 kilometers per second. Those layers contain all the heavy elements created both during the star's life and in the explosion itself. If the original star was even more massive, the core collapses beyond the neutron star stage into a black hole. The critical core mass required for this is probably around 3 times the Sun's mass, though the exact threshold is still a subject of scientific debate. Above that limit, nothing known can stop the collapse. The core shrinks to an infinitely dense point, creating a region of space where gravity is so overwhelmingly strong that not even light can escape. This entire grand cycle, from the initial formation of a star to its eventual death as a supernova or the creation of a planetary nebula, has played out countless times across cosmic history. With 200 billion trillion stars existing at various stages of this intricate evolutionary process, millions are dying every single day across the observable universe. And millions more are simultaneously being born to replace them, ensuring a dynamic, ever-changing stellar population. Let's discuss how we actually measure the immense distances to galaxies, because this measurement capability is absolutely critical for accurately counting them and for estimating the total number of stars. Without precise distances, we simply cannot distinguish between a faint, relatively nearby galaxy and an incredibly bright, but extremely distant one. We wouldn't be able to accurately calculate the vast volume of space we are surveying, and therefore, we couldn't reliably extrapolate from small, observed regions to the entire observable universe. Astronomers use a clever and ingenious set of techniques known as the cosmic distance ladder, a series of overlapping measurement methods that build upon each other, each one extending our reach further into the cosmos. The first rung of this ladder involves direct measurement using a technique called parallax. As Earth orbits the Sun, nearby stars appear to subtly shift their position against the backdrop of much more distant, seemingly fixed stars. The closer the star, the larger this apparent shift. By meticulously measuring that tiny shift, we can calculate the star's distance using straightforward trigonometry. This method works exceptionally well for stars up to a few thousand light-years away. The European Space Agency's Gaia mission, for instance, has measured parallax distances for approximately 2 billion stars within our Milky Way with astonishing precision. However, beyond a few thousand light-years, these apparent shifts become too minuscule to measure accurately, even for an instrument as precise as Gaia. The second rung of the ladder utilizes what are known as standard candles, celestial objects whose intrinsic, true brightness is known with a high degree of certainty. Cepheid variable stars are the most famous and widely used example. Henrietta Leavitt discovered in 1912 that there is a direct and consistent relationship between a cepheid's pulsation period, how long it takes to brighten and dim, and its actual intrinsic brightness. So, by measuring the pulsation period, astronomers can determine how bright the star truly is. Then, by comparing that known intrinsic brightness to how bright it appears from Earth, they can calculate its distance. Edwin Hubble, as we discussed, famously used cepheids to measure the distance to the Andromeda galaxy, conclusively proving that it was an entirely separate galaxy beyond our own. The Hubble Space Telescope has successfully found cepheids in galaxies up to about 100 million light-years away. Beyond that distance, even the brightest cepheids become too faint to detect individually. The third rung of the ladder employs a particular type of stellar explosion, type supernovae. These incredibly powerful events occur when a white dwarf star in a binary system, that is, orbiting another star, slowly accumulates material from its companion. When the white dwarf's mass reaches a critical threshold, approximately 1.4 times the mass of our Sun, it undergoes a runaway thermonuclear detonation, exploding with incredible violence. Because all Type Ia supernovae involve white dwarfs, reaching essentially the same critical mass before exploding, they all possess very similar intrinsic brightnesses. They are also extraordinarily luminous, briefly outshining entire galaxies, which means they can be observed across billions of light years. By carefully calibrating Type Ia supernovae against Cepheid distances in relatively nearby galaxies, astronomers have firmly established that Type Ia supernovae serve as excellent distance indicators for much greater distances. They have been used to measure distances to galaxies billions of light years away. For the most distant galaxies, those approaching the very edge of the observable universe, astronomers rely on a phenomenon called the redshift of light. As the universe expands, light emitted from distant objects gets stretched to longer wavelengths, shifting it towards the red end of the electromagnetic spectrum. The more distant a galaxy is, the faster it is receding from us due to cosmic expansion, and therefore, the greater its observed redshift. By precisely measuring a galaxy's redshift and then applying complex models of cosmic expansion, astronomers can accurately estimate its distance. This method works for galaxies so incredibly distant that no individual stars or even supernova can be resolved. Each rung of this cosmic distance ladder, naturally, has its own inherent uncertainties. Parallax measurements, though precise, have tiny margins of error. Cepheid calibrations aren't absolutely perfect. Type A supernovae show some slight variations in brightness that must be carefully accounted for, and redshift distances depend on complex cosmological models of cosmic expansion, which themselves contain assumptions that are continually refined. However, by meticulously checking each method against the others, and by rigorously quantifying all known uncertainties, astronomers have successfully constructed an incredibly reliable and robust cosmic distance scale. We can measure distances to nearby galaxies with an accuracy of a few percent, and to distant galaxies with perhaps 10 to 20% accuracy. That level of precision is more than sufficient to reliably count galaxies and to estimate the total number of stars within the observable universe. Now, let's explore the remarkable diversity of galaxies, because not all galaxies are flat, graceful spiral disks like our Milky Way. They come in several distinct types, each with unique structures and characteristic stellar populations. Spiral galaxies, as their name suggests, feature a flattened, rotating disk with prominent spiral arms. These spiral arms are typically where active star formation is occurring, making them appear bright and blue due to the presence of young, hot, massive stars. Spiral galaxies also possess a central bulge of older stars and often, like our Milky Way, a bar-shaped structure across their center. Our galaxy is a barred spiral, as is Andromeda, though its bar is less visually prominent. It's important to understand that spiral arms are not rigid, fixed structures. Instead, they are thought to be density waves, regions where stars and gas temporarily bunch up and become more concentrated as they orbit the galactic center. Imagine a traffic jam on a circular highway. Individual cars enter the jam from behind, slow down within the congested area, and then accelerate out of the front. The traffic jam itself, as a pattern, doesn't move around the highway, but the individual cars within it are constantly changing. Similarly, stars enter the spiral arms, spend some time in the denser region, and then leave. The arms persist as patterns, even though the stars flowing through them are constantly changing. Star formation happens preferentially within these spiral arms because that's where interstellar gas becomes compressed. This compression triggers the collapse of molecular clouds, leading to the birth of new stars. This is why spiral arms typically appear bright and bluish. They are teeming with young, hot, massive stars that burn brightly and quickly. Elliptical galaxies, by contrast, possess a very different structure. They are typically ellipsoidal or spherical blobs of stars with little to no discernible disk structure or spiral arms. They range dramatically in size, from small dwarf ellipticals containing only a few billion stars to truly gigantic elliptical galaxies that can boast several trillion stars. These colossal elliptical galaxies are generally thought to form from the cataclysmic mergers of multiple smaller galaxies. When two or more galaxies collide, their individual stars rarely physically hit each other, simply because the distances between stars are so incredibly vast compared to their actual sizes. However, the gas clouds within the colliding galaxies do violently interact and smash into each other. This collision compresses the gas, triggering incredibly intense bursts of star formation. Eventually, the galaxies merge into a single, larger elliptical galaxy. Elliptical galaxies typically contain mostly old stars. They have either used up or lost most of their gas, so active star formation has largely ceased. They glow with the yellowish or reddish light characteristic of older, sun-like stars rather than the brilliant blue light of young, massive stars. Irregular galaxies, as their name implies, lack any clear, defined structure. They are messy, chaotic collections of stars and gas. The Large and Small Magellanic Clouds, which are small satellite galaxies orbiting our Milky Way, are classic examples of irregular galaxies. Many irregulars are small dwarf galaxies. Some are also galaxies that have been gravitationally disrupted and distorted by close interactions with their larger neighboring galaxies. Lenticular galaxies represent an intermediate type, falling somewhere between spiral and elliptical galaxies. They possess a disk, much like spirals, but they exhibit little or no discernible spiral structure and very little ongoing star formation. They are sometimes colloquially referred to as armless spirals or disk ellipticals. The relative abundance of these different galactic types has changed significantly over cosmic history. In the early universe, most galaxies were smaller and irregular in shape. Over immense spans of time, they merged together into the larger spiral and elliptical galaxies that we observe today. Star formation was also much more vigorous in the past. Today's universe contains a greater proportion of large, well-formed galaxies and exhibits less active star formation overall compared to the universe a few billion years ago. When we arrive at our estimate of 2 trillion galaxies, we are counting all these different types, tiny dwarf galaxies with a few billion stars, magnificent spirals housing hundreds of billions, and massive ellipticals with their trillions of stars. Each type contributes to the total stellar count. The sheer diversity means that our chosen average of 100 billion stars per galaxy is just that, an average. Some galaxies, as we've noted, contain far fewer stars, while others contain significantly more. Let's now turn our attention to dark matter and dark energy, because when astronomers meticulously measure the mass of galaxies, they encounter something truly strange and unexpected. The visible stars and gas within a galaxy simply do not account for all of its observed mass. When you measure how fast stars orbit within a galaxy, you can use those speeds to calculate how much total mass must be present to provide the necessary gravitational pull to keep those stars in their orbits. For the Milky Way and other spiral galaxies, the orbital speeds of stars remain surprisingly high, even very far from the galactic center. This observation strongly implies that there is a significant amount of additional mass present, extending far beyond the visible boundaries of the galaxy. However, we don't observe enough stars and gas to account for this missing mass. The visible matter, the stars, gas, and dust that we can directly detect, makes up only about 15% of a galaxy's total mass. The remaining 85% is composed of something entirely mysterious called dark matter. Dark matter is material that does not emit, absorb, or reflect light, or any other form of electromagnetic radiation. We cannot see it directly. We only know it exists because of its powerful gravitational effects on visible matter. No one yet knows precisely what dark matter is made of. It's certainly not ordinary matter, the protons, neutrons, and electrons that make up everything we can see and touch. It's something else entirely, probably some exotic, as yet undiscovered particle that doesn't interact electromagnetically. Several theoretical candidates have been proposed, including weakly interacting massive particles, what IMPAS, axions, and sterile neutrinos. But despite decades of intensive searching, we have not yet directly detected any dark matter particles. Dark matter plays a dramatically crucial role in galaxy formation and structure. Without it, galaxies simply would not hold together, they would fly apart. The visible stars and gas alone do not possess enough collective gravity to keep galaxies bound, given their observed rotation speeds. Dark matter provides the essential extragravitational glue that allows galaxies to exist and remain cohesive structures. When we count stars, we are counting only the visible matter. Dark matter does not form stars. It merely provides the gravitational scaffolding that allows galaxies to form and hold together over cosmic timescales. Dark energy is even more enigmatic and mysterious. Observations of distant Type Ia supernovae in the late 1990s revealed a startling fact. The expansion of the universe is not slowing down, as had been expected due to the gravitational pull of all matter. Instead, it is accelerating. Something utterly unknown is actively pushing space apart, overcoming gravity on the largest cosmic scales. That something is what we call dark energy. Dark energy is estimated to make up about 68% of the total energy content of the universe. Dark matter accounts for about 27%. Ordinary matter, the stuff that makes up stars and planets and us, is only about 5% of the total cosmic inventory. Dark energy profoundly affects the size and evolution of the observable universe. Its accelerating expansion causes space to stretch faster, which in turn affects how far we can see and how many galaxies we can count. It's part of the reason why the observable universe is much larger than 13.8 billion light-years in radius, despite being only 13.8 billion years old. So, when we discuss those 200 billion trillion stars, we are talking about only the visible fraction of the universe's total content. Most of the universe is comprised of dark matter and dark energy, mysterious substances that we still don't fully understand. Stars, despite their vast numbers, represent just a small, luminous fraction of what's truly out there. Let's now discuss globular clusters, because they offer a unique and fascinating window into stellar populations and provide us with a tangible way to visualize immense numbers of stars concentrated together in a relatively small space. Globular clusters are spherical collections of stars, typically containing hundreds of thousands to a few million stars, all tightly packed into a volume perhaps only 100 light-years across. To give you a sense of that scale, that's roughly 588 trillion miles, or approximately 947 trillion kilometers. Our Milky Way galaxy is orbited by about 150 globular clusters, which reside in a vast, spherical halo surrounding the main galactic disk. The stars within globular clusters are incredibly ancient, typically between 10 and 12 billion years old. They formed in the very early days of the galaxy, from gas that was metal-poor, meaning it contained very few heavy elements beyond hydrogen and helium. This characteristic makes globular clusters invaluable laboratories for studying stellar evolution in environments with low metallicity, providing clues about the universe's past. The most spectacular globular cluster visible from Earth's northern hemisphere is M113, located in the constellation Hercules, containing about 300,000 stars. From the southern hemisphere, Omega Centauri is even more impressive, boasting an estimated 10 million stars. Imagine for a moment living on a planet orbiting a star deep within the core of a globular cluster. Your night sky would be an incandescent spectacle, filled with thousands of stars bright enough to easily read by. Some would be so close they might even appear as visible disks, rather than mere points of light suspended against a backdrop of endless stellar fire. The sky would never truly be dark. However, the existence of such planets, especially those capable of harboring life, is highly unlikely. Stars in globular clusters are not only ancient, but also metal-poor. This means they probably didn't have enough heavy elements to form rocky planets in the first place. Furthermore, the frequent and powerful gravitational interactions between so many closely packed stars would rapidly destabilize any planetary orbits, making long-term habitability impossible. So, while globular clusters are undeniably beautiful to behold, they are likely barren of life. When you gaze at a globular cluster through a telescope, you are witnessing, in a very direct way, what a million stars look like when they are concentrated together. It's one of the few ways we can actually visualize a large stellar population, rather than simply understanding it as an abstract number. That dense, brilliant ball of light contains a million individual suns, each one a nuclear furnace like our own, each one potentially billions of years older than our solar system. If you were to multiply that by 200 million, you would approach the total number of stars in the observable universe. Approximately 200 million globular clusters, each like Omega Centauri, would give you a rough approximation of the total stellar count. Let's consider what the night sky might look like from other galaxies, because perspective truly matters when we try to grasp cosmic scale. Imagine an observer in the Andromeda Galaxy looking back towards us. Our Milky Way would be visible as a bright, majestic spiral galaxy, spanning perhaps 6 times the apparent diameter of a full moon in their sky. Individual bright stars would be visible as tiny points of light scattered around our spiral structure. Astronomers on a planet within Andromeda would study the Milky Way in much the same way we study Andromeda, meticulously measuring its rotation, mapping its spiral arms, and searching for individual stars and star clusters. Now, picture yourself in a galaxy a billion light-years away. From that immense distance, our Milky Way would appear as nothing more than another faint smudge among millions, requiring a powerful telescope just to be seen at all. Individual stars within our galaxy would be utterly impossible to resolve. The entire galaxy would be condensed into a single point of light, or a small, fuzzy blob. From near the very edge of our observable universe, even entire galaxies in our local region would be barely visible, even with the most powerful telescopes. Their light would be extraordinarily redshifted and significantly dimmed by the accelerating cosmic expansion. An observer located at that extreme distance would perceive a completely different observable universe, one centered on their location. While it would overlap with a portion of ours, it would also extend far beyond our cosmic horizon in their direction. This highlights an incredibly important point. The observable universe is not the same for all observers. It is defined by how far light can travel in the age of the universe from each specific observer's location. An alien astronomer in a galaxy at our cosmic horizon has their own unique observable universe, distinct from ours, and containing entirely different galaxies that we, from our vantage point, will never be able to see. Therefore, the total number of stars in the entire universe is much larger than the 200 billion trillion we can currently count. We can only count stars within our own observable bubble of space. Beyond that horizon lie countless more stars in other galaxies that we simply cannot see because their light has not yet had time to reach us. If the universe is truly infinite, then the total number of stars is, by definition, infinite. Our 200 billion trillion represents just the finite sample we can observe from our particular location in space and time. Let's consider the rapid rate at which we are continuously discovering new information about stars and galaxies. The pace of discovery has accelerated dramatically in recent decades. Before 1995, for instance, we knew of no planets outside our solar system. Today, we have confirmed over 6,000 exoplanets, and that number continues to climb almost daily. Before the Hubble Space Telescope, we had only very rough estimates of galaxy counts. Now, we have detailed surveys covering millions of galaxies across vast stretches of the cosmos. Before the Gaia mission, our stellar distance measurements were limited. Now, we possess precise positions and distances for over 1 billion stars within our own galaxy. The James Webb Space Telescope, which became fully operational in 2022, is pushing these boundaries even further. It is finding galaxies at extreme distances, allowing us to see further back in cosmic time than Hubble ever could. Early results from JWST have already revealed surprisingly massive, well-formed galaxies existing much earlier in the universe's history than our previous models predicted. This is causing astronomers to revise their theories of galaxy formation and evolution. Future telescopes will undoubtedly continue this trend of unprecedented discovery. The upcoming Extremely Large Telescope, ELT, for example, will boast a colossal 39 meters, 128-foot mirror, collecting significantly more light than any current optical telescope. The Nancy Grace Roman Space Telescope will survey enormous areas of the sky, discovering millions more galaxies. Each new instrument refines our cosmic census of stars. Each new discovery adjusts our estimates slightly. The number, 200 billion trillion, will undoubtedly be updated as better data becomes available, but the overall order of magnitude is highly unlikely to change drastically. We are counting stars within the correct ballpark, even if the exact numerical value shifts slightly as our measurements improve. This progressive refinement is a fundamental characteristic of how science operates. We make the best possible estimates we can with the currently available data, and then we continuously improve those estimates as new, better data arrives. The number of stars isn't some wild speculation, it's a measurement-based estimate with carefully quantified uncertainties that will continue to improve over time. What we do know with absolute certainty is that the universe is utterly filled with stars in quantities that truly boggle the human mind. There are more stars than grains of sand on all of Earth's beaches. More stars than humans have ever collectively gazed at in the night sky since our species first emerged. More stars than we could ever hope to visit, even if we had billions of years and could travel at the speed of light. And perhaps most remarkably, we, as a species, figured this out. We conceived and built telescopes, launched satellites, and developed sophisticated detectors sensitive enough to count galaxies billions of light years away. We developed the complex mathematics required to calculate distances across these immense cosmic scales. We created intricate theories that explain what we observe and that make testable predictions for future discoveries. That incredible intellectual achievement, measuring the contents of the observable universe from one small planet orbiting one ordinary star, represents one of humanity's greatest accomplishments. We are tiny and brief in cosmic terms, but we are also uniquely capable of comprehending the very vastness that contains us. That capacity for profound understanding is truly extraordinary. We are conscious matter that can contemplate the cosmos. We are the universe's way of knowing itself. That in itself is remarkable and beautiful, and profoundly worth celebrating. So, when you look up at the stars tonight, remember what you now know. Those visible stars are merely the nearest few thousand of an astonishing 200 billion trillion. Each twinkling point of light represents a massive nuclear furnace, most likely surrounded by its own retinue of planets, potentially even harboring life. Each one is a part of the grand cosmic web of galaxies and structures stretching across billions of light years. We have measured this. We have counted them. We have, in a profound sense, grasped our own place among this immense multitude. That is remarkable. That is extraordinary. And that is what, in part, makes us human. But let's go even deeper into several specific phenomena that truly reveal how dynamic, how interconnected, and how vibrantly alive this stellar population truly is. Understanding binary stars, witnessing stellar nurseries in action, exploring the most extreme objects in the cosmos, and appreciating how galaxies interact and influence each other will transform your appreciation for what those 200 billion trillion stars actually do and how they evolve over cosmic timescales. Most stars do not exist in isolation like our Sun. The vast majority, in fact, reside in binary or multiple star systems, where two or more stars orbit each other, gravitationally bound for billions of years. In a binary system, two stars perform an intricate gravitational dance around their common center of mass, a cosmic ballet that can endure for the entire lifetime of both stars. These systems are incredibly common. Roughly half of all Sun-like stars are believed to exist in binary or multiple star systems. For more massive stars, this fraction is even higher, perhaps 70 to 80%. Some binary systems are wide, with the two stars separated by hundreds of astronomical units. An astronomical unit is the average distance between the Earth and the Sun. So, we're talking about 100 to 200 times Earth's distance from the Sun, or roughly 9,300,000,000 miles to 18,600,000,000 miles, approximately 15 billion to 30 billion kilometers. These widely separated stars orbit each other over thousands of years and typically have very little influence on each other's individual evolution. Other binary systems, however, are close, with the stars separated by only a few times their own diameters. These tight systems are particularly fascinating because the stars can actually exchange material. If one star swells up into a red giant, its outer atmosphere might spill over onto its companion star. This process of mass transfer can dramatically affect the evolutionary paths of both stars. Some extremely close binaries are so tightly bound that the stars actually touch, sharing a common envelope of gas. These contact binaries often resemble a cosmic peanut, with two stellar cores merged together, but each maintaining its distinct identity. Binary star systems are responsible for some of the most spectacular and energetic events observed in astronomy. Type Ia supernovae, which we previously discussed as crucial distance indicators, specifically occur in binary systems where a white dwarf star slowly accumulates material from its companion until it reaches that critical mass and explodes. Nova outbursts are another fascinating phenomenon that occurs in binary systems. These happen when a white dwarf in a binary system accretes hydrogen from its companion. The hydrogen gradually builds up on the white dwarf's incredibly dense surface until the conditions are just right for a sudden, explosive burst of nuclear fusion. The white dwarf briefly brightens by thousands of times, appearing as a new star in the sky, hence nova, meaning new in Latin, before fading back to its normal brightness, only to repeat the cycle years or decades later. Some of the most massive stars in the universe exist in binary systems where both components are giants. When one of these massive stars explodes as a supernova, the explosion itself can be asymmetric, imparting a powerful kick to the remnant neutron star or black hole, sending it hurtling through space at hundreds of miles per second. The remaining companion star might be severely disrupted by this event, or it might continue orbiting the compact remnant, now a lonely cosmic traveler. Binary systems serve as a powerful reminder that stellar populations are highly interactive. Stars don't simply shine in isolation, they gravitationally and sometimes physically interact exchanging material, influencing each other's evolutionary paths, and creating phenomena that we would never observe in single star systems. With 200 billion trillion stars in total, and roughly half of them existing in binary or multiple systems, we are talking about approximately 100 billion trillion binary systems. Each one of these is unique, with different mass ratios, different orbital periods, different ages, and existing in different stages of their complex evolution. The sheer diversity within this population is truly staggering. Now, let's take a more detailed look at stellar nurseries, because these are the cosmic factories where those 200 billion trillion stars were born, and where new stars are continuously being created even as we speak. The Eagle Nebula, famously immortalized by the Hubble Space Telescope's pillars of creation. UMAGE is an incredibly active star-forming region located approximately 7,000 light-years from Earth. That's roughly 41 quadrillion miles, or about 66 quadrillion kilometers away. Those towering, ethereal pillars of gas and dust that dominate the Eagle Nebula image are several light-years tall, roughly 18 trillion miles, or 29 trillion kilometers. They are simultaneously being eroded by the intense ultraviolet radiation blasting forth from nearby massive, young stars, while also serving as protected birthplaces for brand new stars. Inside those majestic pillars, dense clumps of gas are slowly but surely collapsing under their own immense gravity. Some of these clumps have already formed protostars, infant stars not yet hot enough to ignite nuclear fusion. These protostars are typically surrounded by swirling disks of gas and dust, known as protoplanetary disks, where planets will eventually coalesce and form. The process of star formation in these nurseries is often violent and dynamic. Powerful jets of material frequently shoot out from the poles of the protostars, plowing into the surrounding gas and creating glowing shock waves. These energetic jets are driven by powerful magnetic fields that thread through the accretion disk. As material spirals inward onto the protostar, it generates intense magnetic fields that then channel some of the infalling gas back outwards along the rotational axis, ejecting it at speeds of hundreds of miles per second. The Carina Nebula is another spectacular star-forming factory, home to some of the most massive stars known in our galaxy. Eta Carinae, possibly the most massive binary star system in our region of the galaxy, contains a star that is over 100 times the mass of our Sun. It is so incredibly massive and luminous that it is inherently unstable. In the 1840s, Eta Carinae underwent a massive outburst, ejecting several times the mass of our Sun into space and briefly becoming one of the brightest stars in the entire sky, despite being 7,500 light-years away. That's roughly 44 quadrillion miles, or approximately 71 quadrillion kilometers. Eta Carinae is expected to explode as a supernova sometime in the astronomically near future, perhaps within the next 100,000 years. When it does, it will briefly outshine the full moon, even at its vast distance, and the explosion will be visible even during daylight hours from Earth. The Orion Nebula, which is visible to the naked eye as a fuzzy patch in the sword of the constellation Orion, is the closest major star-forming region to us, located about 1,300 light-years away. That's roughly 7.6 quadrillion miles, or approximately 12.3 quadrillion kilometers. It contains about 700 stars in various stages of formation, ranging from protostars still deeply embedded in their natal gas clouds to young stars less than 1 million years old. The Trapezium cluster, situated at the nebula's very heart, contains 4 exceptionally bright, massive stars that are easily visible even through small telescopes. These stars are only about 1 million years old, yet they already shine with the collective light of hundreds of thousands of suns. Their intense ultraviolet radiation ionizes the surrounding gas, causing it to glow, thus creating the stunningly beautiful nebula that we observe. In a few million years, this gas will be completely dispersed by powerful stellar winds and radiation, leaving behind an open cluster of stars, much like the famous Pleiades. Eventually, over tens or hundreds of millions of years, gravitational interactions will cause the cluster to slowly dissolve, scattering its individual stars throughout the wider galaxy. This grand cycle of stellar birth, life, and dispersal plays out across the entire universe. Molecular clouds collapse, new stars form, and the most massive stars quickly ionize and disperse the remaining gas. A stellar cluster emerges, which then, over time, dissolves. The stars spread out, becoming part of the general galactic population. Eventually, some of these stars die, returning their processed material to space, thereby enriching future generations of clouds that will, in turn, collapse to form new stars. Star formation rates have varied dramatically over the long course of cosmic time. As we mentioned, the peak of star formation occurred about 10 to 11 billion years ago, when galaxies were generally smaller, denser, and far richer in gas. Back then, the universe was producing stars at perhaps 10 times the current rate. Since that ancient peak, the rate of star formation has steadily declined. Much of the available gas has either been consumed by previous generations of stars or dispersed into the vast intergalactic medium. What remains is often in more diffuse reservoirs that form stars less efficiently. The universe today produces perhaps only 1/3 as many new stars per year as it did at its peak. This decline will continue. In a trillion years, most galaxies will have exhausted their gas reserves, and star formation will largely sputter out. The very last stars will form, and then no more. The existing stellar population will age and gradually fade as the long-lived red dwarfs slowly burn through their fuel over trillions of years. But that future is so incredibly far away, it's almost impossible to truly grasp. For now, and for billions of years to come, stellar nurseries across the cosmos continue their work, constantly producing new stars. Our count of 200 billion trillion stars includes stars at all ages, from newborns less than 1 million years old to ancient stars that formed when the universe itself was less than 1 billion years old. Let's now turn our attention to quasars and active galactic nuclei, because these spectacular and exotic objects represent some of the most extreme stellar environments in the universe and played a profoundly crucial role in shaping the early evolution of galaxies. A quasar is essentially a galaxy with an intensely bright core, powered by a supermassive black hole that is actively accreting, or drawing in, vast amounts of material. This central black hole, typically weighing a few million to several billion times the mass of our Sun, resides at the very heart of the galaxy. As gas spirals inward towards the black hole, it forms an incredibly hot accretion disk, heated to millions of degrees by friction and intense gravitational forces. This blazing disk can actually outshine the combined light of an entire galaxy's worth of stars, making the quasar visible across billions of light years. Quasars were far more common in the early universe, but are relatively rare today. Most formed when galaxies were young and still rich in gas, providing an ample and continuous fuel supply for their central black holes. As galaxies aged and consumed their available gas, quasar activity naturally declined. Today's universe has far fewer active quasars compared to the universe a few billion years ago. The brightest known quasar, J100-182, contains a black hole with an astonishing mass of about 12 billion times the Sun's mass. This colossal black hole formed when the universe was only about 900 million years old. How a black hole managed to grow so massive so quickly remains a significant puzzle for astronomers. It implies extremely efficient accretion over a relatively short cosmic timescale. Quas brightest stars in the entire sky, despite being 7,500 light-years away. That's roughly 44 quadrillion miles, or approximately 71 quadrillion kilometers. Eta Carinae is destined to explode as a supernova sometime in the astronomically near future, perhaps within the next 100,000 years. When it does, it will briefly outshine the full moon despite its vast distance and will even be visible during the day. The Orion Nebula, which you can see with your naked eye as a fuzzy patch in Orion's sword, is the closest major star-forming region to us, located about 1,300 light-years away. That's roughly 7.6 quadrillion miles, or approximately 12.3 quadrillion kilometers. It contains about 700 stars in various stages of formation, from protostars still deeply embedded in their natal gas clouds to young, brilliant stars less than 1 million years old. The trapezium cluster, at the very heart of the nebula, contains 4 bright, massive stars, easily visible even through small telescopes. These stars are only about 1 million years old, but they already shine with the combined light of hundreds of thousands of suns. Their intense ultraviolet radiation is ionizing the surrounding gas, causing it to glow, creating the stunning nebula we observe. In just a few million years, the gas will be completely dispersed by powerful stellar winds and radiation, leaving behind an open cluster of stars much like the Pleiades. Eventually, over tens or hundreds of millions of years, gravitational interactions will cause the cluster to slowly dissolve, scattering its individual stars throughout the galaxy. This grand cycle plays out repeatedly across the entire universe. Molecular clouds collapse. Stars form. The most massive stars quickly ionize and disperse the remaining gas. A beautiful stellar cluster emerges. Over time, that cluster dissolves, and its stars spread out. Eventually, some of those stars die, returning their processed material to space, enriching future generations of clouds that will, in turn, collapse to form new stars. Star formation rates have varied dramatically over cosmic time. The peak period occurred about 10 to 11 billion years ago, when galaxies were smaller, denser, and far richer in gas. Back then, the universe was forming stars at perhaps 10 times the current rate. Since that peak, star formation has steadily declined. Much of the available gas has been consumed or dispersed. What remains is often in more diffuse reservoirs that are less efficient at forming stars. The universe today produces perhaps 1/3 as many new stars per year as it did at its peak. This decline will continue. In 1 trillion years, most galaxies will have exhausted their gas reserves. Star formation will finally sputter out. The last stars will form, and then no more. The stellar population will age and gradually fade as long-lived red dwarfs slowly burn through their meager fuel reserves over trillions of years. But that future is so incredibly far away, it's almost meaningless to us now. For now, and for billions of years to come, stellar nurseries across the cosmos continue to produce new stars. The 200 billion trillion count includes stars at all ages, from newborns less than 1 million years old to ancient stars formed when the universe was less than 1 billion years old. Let's discuss quasars and active galactic nuclei, because they represent the most extreme stellar environments in the universe and played a truly crucial role in shaping the evolution of galaxies. A quasar is essentially a galaxy with an extraordinarily bright core, powered by a supermassive black hole that is actively accreting, or feeding, on vast amounts of material. This central black hole, typically ranging from a few million to a few billion times the mass of our Sun, resides at the very heart of the galaxy. Gas spiraling into the black hole forms an accretion disk, which is heated to millions of degrees by friction. This incredibly luminous disk can actually outshine the combined light of an entire galaxy's worth of stars, making the quasar visible across billions of light years. Quasars were far more common in the early universe, but are relatively rare today. Most formed when galaxies were young and gas-rich, providing ample fuel for the central black hole to grow rapidly. As galaxies aged and consumed their gas in star formation or blew it away, quasar activity naturally declined. Today's universe has relatively few active quasars compared to the universe a few billion years ago. The brightest known quasar, J1R+282, contains a black hole about 12 billion times the mass of the Sun. This colossal black hole formed when the universe was only 900 million years old. How a black hole managed to get that massive so quickly is still a significant puzzle for astronomers. It requires incredibly efficient accretion over a relatively short cosmic time. Quasars profoundly affect their host galaxies. The immense energy output from the accretion disk drives powerful winds that can blow gas out of the galaxy at thousands of miles per second. This process effectively quenches star formation by removing the raw material needed to make new stars. This feedback mechanism is thought to regulate galaxy growth. Without it, galaxies would likely convert all their gas into stars very quickly. The quasar phase acts as a self-limiting process. The black hole grows by accreting gas, which powers winds that then blow away the remaining gas, effectively shutting off both star formation and further black hole growth. Most massive galaxies, including our own Milky Way, contain supermassive black holes at their centers. Ours is about 4 million times the mass of the Sun. It's currently quiescent, meaning it's not actively accreting much material, but in the past, it almost certainly went through an active phase when it was feeding vigorously and possibly shining as a quasar. Evidence of this past activity appears in the Fermi bubbles, two enormous lobes of hot gas extending 50,000 light-years, about 294 quadrillion miles, or approximately 473 quadrillion kilometers, above and below the galactic plane.